just to let everyone know. We do have a few more booked in, so I'll just give it a couple more minutes to see if anybody shows up a minute or two late. But yeah, thank you very much indeed for joining us for this next on our PHINZ webinar series. We are going to be talking about heat pumps, good old heat pumps, heating, cooling, hot water. How do we specify them? How do we design them? How do we put them into PHPP? Hopefully, I'm going to get some insights out of this because I've been fighting with heat pumps for the past few days. So I'm quite looking forward to seeing what comes out of this. So we will crack on, I think. Oh, here's another one. Cool, Nikki, if you don't mind just loading people in as they arrive, that'd be awesome, please.
Yep.
Cool. Okay, well, a little bit of housekeeping. So we get Passive House Institute CPD points for this session, so you'll get an email afterwards with the code to put in for that for those that need it. We're also really happy to be partnering with NZIA and NZRAB, so you get 15 NZRAB points for this. So make sure you get those. If you'd like to submit any questions, there should be a chat box at the bottom of your bar, or Control Alt and H on your T-Guard. And yeah, when questions start popping in, if you give them a like, so the ones with the most likes can pop to the top of the list, and then we'll know what to talk about. We're going to have a 30-minute Q&A session after 3 20-minute presentations, which should be awesome. So first of all, thank you so much for our sponsor, Stiebel Eltron. I'm sure most people on the call have heard of them, but they do a range of fantastic products, whether they're heat pumps, ventilation systems, hot water systems. But they also do fantastic work around education and advocacy for lower energy, higher performance buildings. Been around since 1924, which is pretty cool. And there's some pretty epic looking old school devices on there next to the new ones. And they've got some new ones coming out, I know, as well. So that's pretty exciting. I'm Joe. I'm the chair of PHINZ. I won't talk about that much, but I'm a certified passive house designer. So I know a bit, but not everything. And today we have all these lovely people presenting. So first of all is Bhavesh from Stiebel Eltron. He's a technical engineer. We've got Carolyn, who's policy and regulation specialist, and Catherine, who's a senior advisor, standards and technical from ECA. I just nicked that title from your LinkedIn profile, I'm afraid, Catherine, so I hope that's right. And then we've got Jason Quinn from Sustainable Engineering, all-round building performance expert. So I'm going to hand over to our first presenter, Bhavesh. We're going to go through the 3 presentations and we'll have a QA at the end. So if you do have any questions, bang them in the chat. And yeah, looking forward to seeing how this goes. Do you want to share, Bhavesh?
Mm-hmm. Cool. Can you see it all right? Perfect, thank you. Thanks. So thanks for the introduction. Welcome everybody. My name is Bhavesh. As Joe mentioned, I've been working as a technical manager in Stiebel Eltron in New Zealand for about 6 years. Before that, I was in Germany in the headquarters there at the back. That's our energy campus. I worked in Germany for about 6 years again. I've lived in Germany for 15 years before coming here. So all the reason basically to come here was to educate a bit about the heat pump system, the energy efficiency side of it, and bring that heat pump into mainstream market, right? So which I'm fascinated to do that. I love doing this, and it's just one of my passions. So today I'll speak a bit about basics of heat pumps. So what are heat pumps? There might be a bit of misconceptions about heat pumps, or people might not know exactly how it works. So it's sort of basically go through it. But so starting off with that, there are different types of heat pumps. So what are different types of heat pumps? Heat pumps that can be basically categorized under 3 different types. It's basically air source heat pump, water source heat pump, and ground source heat pump, right? The only difference actually between them is where do you get that energy from? It's the medium of heat exchange. So air source heat pump gets most of the energy from the air, or all of the energy from air actually, and ground source gets from the ground or brine, and water source gets from water. That's only the technical difference between them. The refrigerant cycle, we'll talk about it a bit later, is exactly the same, and those are the only differences. So the most common used heat pump that we see, including our high wall heat pump, it's famous in New Zealand, or hot water heat pumps, these are all types of air sourced heat pumps. And these air source heat pumps are basically come in 2 designs. One we call a monoblock heat pump, and the other type is called split heat pumps. So the monoblock heat pump is a heat pump that we've got all the components, we'll talk about a bit later, different components of heat pump, all the components are in one body. It's basically comprised in one body, hence the name monoblock system. And split system, as the name suggests, is splitted. So those components are splitted into different parts. So if you imagine a high wall heat pump that you probably most of you got in your homes for any lounge or bedrooms. So those have two components. One part of the component is outside, that's the fan unit. The compressor is, and the evaporator is. And there's a refrigerant line running between the outdoor unit and the indoor unit. And the indoor part, the fan coil part, is which blows out hot air or cold air. That is the condenser. So it's basically split between inside and outside, hence the name split units. Of course, it offers flexibility, so you can actually place that indoor unit wherever you want. But of course, you need a refrigeration professional to install that system. So in air source heat pump, two types of heat pump, monoblock and split systems. Moving on with the heat pump. So what is actually a heat pump? So as the name suggests, heat pumps is actually a pump. It's a pump that moves the environmental energy from one place to another. So in this case, it basically moves the heat rather than creating it. As we know from thermodynamics, you cannot create energy nor destroy it. You basically are moving from one place to another. And so what the heat pump does is it moves the energy counter to the direction of normal flow. So normally energy moves from basically warm to cold. So in this case, heat pump does work to move the energy counter, but that means from cold to hot. So basically moving from cold to outdoors in winter, to move the heat inside the house. It's named pump. So most of the heat pump also have what we call the reversing valve. So you can use that in summer to use it for a cooling mode. So the same heat pump works in winter for heating, and exactly with the reversing valve, we can use that heat pump to move it to cooling in summer. Most of the heat pumps work over a range of temperatures, so anywhere between -20 and +40 degree, which makes it useful to work in most part of the world. So how does the heat pump work? Heat pump is nothing more than a refrigerator, actually. It's just exactly how a refrigerator works. As a matter of fact, refrigerators and air conditioners are example of heat pumps just running in cooling mode. So if you imagine a refrigerator, you've basically got your food inside that. So what that refrigerant cycle does is it extracts the energy from that food, thereby cooling it down and dumps it at the back of the refrigerator. So you've got a little fan at the back of the refrigerator, or that basically is warmer than the inside. So it basically gets the energy from inside and dumps it at the back. All right, so heat pump basically in that case uses the free heat from sun, which is stored in air, ground, or water, and concentrates in a smaller area, that is the apartments or house, for space heating and domestic hot water. So basically a little bit about heat pumps. So this could be a bit technical, but I'll try my best to sort of explain that to you. This is the main sort of part of heat pump. As you can see, there are four components. So you've got this one component, evaporator, compressor, your condenser, and expansion vessel. So it's basically hermetically sealed cycle. Inside this hermetically sealed cycle, what we have is refrigerant flowing, right? And this refrigerant has one really special characteristic. It boils at extremely low temperature. So, for example, we know that water boils at 100 degrees Celsius. We've got refrigerant like R134A, for example, in some of our hot water heat pumps that boil at -26 degrees. And we've got a 410A, which actually boils at -48 degrees, so extremely low boiling point. So what then happens is any temperature that we get here, especially in New Zealand, even Queenstown, if -6 degrees comes here, the refrigerant starts boiling. So as the refrigerant boils, it makes its way to the compressor. So the compressor gets basically evaporated, or vapor refrigerant, we call it, and compresses it, thereby increasing the pressure and temperature. So then what happens is that hot gas, we call it hot gas, goes into the condenser, where we have colder water coming from one side, and that becomes way hot on the way out. So that can be used for heating system, potable hot water heating, pool heating, spa heating, anything you want, right? So that energy is lost here, given out here, and then the refrigerant makes its way to the expansion vessel. So it still is pressurized. So what happens here in that expands basically expands that, thereby releasing the pressure out of it and making it cooler, and the whole cycle starts again, right? So that basically the only energy that is given in the heat pump is here in the compressor. So most of the energy is received here, and the only electrical energy that the heat pump requires is in the compressor. So if you look at it that way, so why is it that the heat pump is so efficient? So you can see that most of the energy that we receive from air, groundwater, or ground, that's about 75% to 80% energy is what we receive. That's basically quote unquote free energy for us, right? And only about 20 to 25% is required for electricity. So good thing about it is you can actually even produce that or part of that electricity by yourself with solar PV or wind turbine or the rest of it, right? So you've got about 75 to 80% of the environmental energy, put 20 to 25% of the electrical energy to make into 100% heating system. So if you calculate the coefficients of performance in that case, or COP, the efficiency of the heat pump is the heat output given out here, 100%. By the work input, how much you put in here is 25%, which gives you your COP of 4 or 400% more efficient than just using electrical element. So heat pump again, as briefly mentioned before, can be used in summer for cooling. So that means all it does is changes what you've learned, the evaporator and the condenser parts. So you're basically extracting the energy from your indoors, thereby cooling it down, and we dump the energy outside, right? In winter, of course, it extracts the energy from the ambient air and dumps it inside, or thereby heating the house. The same heat pump can be reversed to heat and cool the space. Slightly product overview of heat pumps that we have and that can be used. So three heat pumps on the right. You can see here those heat pumps can be used for space heating, hot water heating, pool heating, spa heating, depending on the size of your building. And these ones here, these are just hot water heat pumps. So you can see here is a hot water cylinder here on the heat pump on the top, which has got a really smaller compressor of only about 500 watt. Hence it's quite efficient. And that basically heats up the tank to produce a potable hot water. We also have ground source heat pump, basically similar size. We don't need a fan here because we're extracting the energy from ground source or water source in the size of 4 kilowatt to 90 kilowatt for sort of residential purposes and semi-commercial purposes. The application areas of the heat pump, as you might have guessed, we basically produce hot water, and that hot water can be used in most cases. For example, in this case, you could use that for underfloor heating system, for radiator systems, to produce your potable hot water, to heat the swimming pool and spa. You can actually even reverse the cycle, as you've learned, to utilize it for passive cooling. So you've got your underfloor heating anyway, so you can introduce cooler water in summer to avoid house from overheating or even slightly cool down the house. And also you can use the active cooling via fan coil systems to cool the house. And the good thing about it is that heat pump also connects to solar PV. So in summer, mostly in summer, when you're producing the electricity when the sun is out, actually you can run the heat pump to cool down the house or produce hot water. It's quite a cool concept. So our focus as a company is quite clear. So we promote energy transitions with products that we've been making since over 100 years. We are an expert in heat pump. We've been producing heat pump in Germany for almost 50 years. 1976 was this yellow retro looking, as Joe mentioned, heat pump that was the first one we produced in 1976. We've got our expertise in ventilation as well. Been doing ventilation for more than 25 years. So a company actually really aligned with the energy transition that we're going through at the moment. I'm proud to be working for the company. So we've got a bit of a scenario analysis I did a couple of years back. So what I wanted to sort of see when I came to New Zealand was how much of energy actually could we save implementing heat pump and replacing an existing electrical hot water cylinders that we might have at home or gas hot water systems that we might have for them. So what would be the energy savings that we can make, and how can we use this? So was my thought, right? So because I've always heard that, okay, New Zealand is really green national grid, electricity production is over 85%, which is awesome. But there are also a couple of things that we probably need to know about before we call ourselves a really green country, right? So I fished out some information from MB website and sort of came to this, made this report out of it. Our national energy consumption as whole is about 167 or 66 terawatt hours is how much we consume as energy. That includes the electricity, that includes petrol, gas, everything we have, right? So it's about 167 terawatt hours. And if you look at by energy used by sector, we can see that transport consumes the most amount of energy, about 36%, and that's basically oil, right? So petrol there. And the next second biggest one is basically your industry, consumes a lot of energy as well. And domestically, so for domestic purposes, we consume about 11% of energy. That means the electricity to heat and cool the house, your gas to cook, and also, produce hot water. So that's about 11%. So if you look at that chunk, it's only about, so 11% is about 18 terawatt hours is what you use energy that we use for domestic purposes, right? Now, if you see by energies by source, so how do we get our energy, right? So we are proud that our electricity grid is 85% renewable, but that 85% is actually only about 24% of the total energy that you use, right? So the most of the energy that you use as a country is oil. That is because we've got transport heavy, so about 36% transport. So we use 48% oil, 12.5% gas. So that's about 60% plus fossil fuels. We've got a few renewable here, but in electricity, it's let's say 24%, right? So if you look at the total national electricity consumption out of 167 terawatt hours, we're talking about almost 40 terawatt hours is how much of electricity that we consume as a country. So now let's bring that down again to by sector. So how much of electricity is used in each sector? In this case, most of the electricity is used in residential. So 32% of the electricity is used in residential, 24% in commercial, and the rest of it in other industries. So the 34% of electricity is about 12.7 terawatt hours of electricity is what we use in residential, right? So out of that 12.7 terawatt hours, you can see here that electricity is used for space heating. So your heat pumps, basically panel heaters, for refrigeration, for hot water, is 29%. So 29% of that 12.7 terawatt hours, which is 5.3 terawatt hours, is used to produce hot water. And I thought, okay, what could we do that if we could make this hot water production very efficient? How much would we save? So that's one part of the report, and the second part is I also wanted to combine these two parts, and I wanted to look at what is the fleet of vehicles that we have in New Zealand. So you can see that the cars that you and I ride every day, probably the light passenger vehicles or LPV cars, we've got about 3.4 million of those for 5.5 million people, right? 3.4 million cars in New Zealand. That includes about 38,000, probably now 42,000 EVs that we have. So 3.4 million. And those 3.4 million LPVs cover about 33 billion kilometers a year. So we travel 33 billion combined in a year in New Zealand. So if you look at that 33 billion kilometers that you travel and see how much of CO2 that actually emit per in traveling those kilometers, it's about 7.1 metric ton, 7.1 million ton of CO2 that we actually emit just with our passenger vehicles, right? So my idea was now, if we can actually save that, so if you could replace the electric hot water cylinders with hot water heat pumps, right? Of course, a fictive scenario, but if we could replace all of it, how much of energy would you save? So because we know now that the hot water uses quite a lot of energy. That's about 29% of the total energy required in the households. And if you replace that electric hot water cylinders and gas caliphones with hot water heat pump, the savings would be about 2.7 terawatt hour of electricity per year, or about 7% of total electricity that we generate in New Zealand, right? And that electricity actually would support about 1.4 million EVs without needing to produce any electricity further. So no dams, no Lake Onslow, no more sort of wind turbines, solar farms. Of course, you can do that, but we could support so many EVs, 1.4 plus million EVs, without producing any power, right? And that would actually replace about out of 33 billion kilometers, about 14 billion kilometers travel, just by saving that electricity and replacing those old technology with a newer one. So, and that was quite an eye opener for me. And I ran that past to a couple of engineers in ICA and some other really sharp brain people with good brains as well, so they're probably approved of that. And it is quite a lot of savings that we can make here. And the last but not the least is so with that emission, so how much with that 7.1 million ton of carbon dioxide that you normally emit in the atmosphere, 3 million could be saved if you can actually run EVs, right? So 3 million can be saved, and 3 million is about running a 500 megawatt coal-fired power plant, right? And just to give an example, Huntley is only 953. So actually, it is quite a lot of CO2 you can save. And of course, if we don't meet our carbon goals as a country, we'd have to purchase international carbon credits, right, just to offset our emissions. And these are the carbon credits that we sort of need to play depending on where we are. So if you're sort of complying on the Paris Agreement, it's about $20 US per ton of carbon dioxide. So for 3 million ton, we're talking about 60 million US, which is about 106 million using dollars. And that would, so that's basically each year, right? And that would fully subsidize installation of 13,000 hot water heat pumps, or partially subsidize 26,000 or more heat pumps. So you can keep on building on that. You know, you can keep the money in New Zealand, not send it offshore. And I thought that was quite a good idea to do that. And just the amount of savings that you can make through it was just mind blowing for me. And I just sort of wanted to show it. It might look really nice, and you know, it's just the backup at your backyard. The heat pump might look sort of, you know, pretty nice and simple, but it has quite a lot of potential if we sort of implement in a bigger market. Is what I wanted to show here. And no, that's from me. Any questions you can probably ask now or later, whenever you feel comfortable.
Awesome, Bhavesh. Thank you very much. Yeah, we'll save the questions for the Q&A at the end. Thank you. But I heard that statistic when you published that report, and it's absolutely mind-blowing. You know, just swapping out hot water cylinders, we wouldn't have to build 2 power stations or something. So it's significantly more cost effective for the government to subsidize a program like that rather than building some other massive things that will take, you know, 40, 50 years to actually put into production. So come on, government, subsidize something sensible. Awesome. Thank you very much indeed. So as I say, keep your questions to the end, bang them into the chat. And I'm going to hand over to Carolyn and Catherine from ECA now. Thank you very much.
Awesome. Thank you very much. So I'm just going to pop up some slides as well. So just give me one moment to do that. Right. Can everyone see that?
We're seeing your yeah, beautiful. There we go. Thank you.
Awesome. Excellent. Thank you very much. I'm going to talk today about our ECA's heat pump water heater research program. So I am Carolyn Shivanandan, and I've also got with me Catherine May, who's the project manager for this piece of work. So I think she's going to cover off a few of the slides as well. But today I'm going to briefly talk about who is ECA and why are we interested in this area. We're also going to talk about our, I guess, a high-level explanation of the research project that we've got ongoing at the moment, and cover off some of the initial high-level findings from that we've found so far. So hopefully that will be interesting to you all. So first of all, who is ECA? So we are a Crown agency. We are 25 years old this year. We have a mandated role to look at, to focus on energy efficiency. We also focus on empowering energy users, and that includes things like demand flexibility and also accelerating renewable energy. So we're a regulator. We also have a role in providing information and resources to people, and we also have a targeted investment and support lever as well. So, yeah, first of all, I guess, why are we interested in hot water? So as Bhavesh kind of sort of mentioned, hot water is really kind of a key user of energy in the residential space. So I've got a couple of pie graphs here. So the left-hand one, I guess what we're saying here is that around about a third of residential energy use is hot water. So that's, I guess, quite a big area if you're looking to reduce energy use in the home. And then the other thing is that we think that there's potential to do something about it. So the pie graph on the right just talks about the types of water heaters used in New Zealand at the moment. So as you can see, about 3/4 of them are electric storage water heaters. So that's kind of your old school hot water cylinder. We've got about 1/4 is gas instantaneous, and then everything else is that kind of tiny sliver. So, and that includes heat pump water heaters, which are kind of less than 1% of the market at the moment. So we're interested in, what are the barriers to that? Is it about capital costs? Is it about awareness? Is it about installer training? There's also, I guess, limited real world performance data, and particularly in low temperature conditions that we have in New Zealand in winter. So there's a few things that we're wondering about. Well, what are the barriers? What are the gaps? What can we do? So this slide, just also talking about this is, I've just cribbed this. We've cribbed this from the ECA website. These are a sort of a graphic that it was put together before we started this project, but I guess the key point here is that hot water heat pumps have the cheapest cost of ownership compared to the kind of mainstream electric storage water heaters and gas continuous flow. The big point really is that sort of blue piece at the bottom, which is the installation cost is higher, and the ongoing running cost or the fuel cost over 10 years is a lot less than any other option. We are wondering if maybe there are some kind of barriers around the people who are purchasing these or specifying these, builders, landlords, specifiers of various sorts. They're not the ones paying the ongoing running costs of these products. So, maybe there's a barrier there. So those are all questions that we are interested in finding out more about. I guess the other thing is, what to choose. There seems to be a wide range of products on the market. So, there is obviously, split systems, integral systems, different sizes, different configurations, different types of installation. And so we wanted to understand more about how different types perform and what was suitable for different scenarios. So all of this led us to the research project that we are working on now. I'll hand over to Catherine for, she's going to just run us through exactly what we're looking at and what we've found so far.
Thanks, Carolyn. So as Carolyn mentioned, we're undertaking a bit of a research project to understand a bit more about the performance of heat pump water heaters in general, how different products compare to each other across the different types, and how the technology also functions in different climate zones and household types as well. So we've installed about 80 products in homes across the country, and we're going to monitor them for about 12 months to see how they go. As you'll see on the slide there, we've split the country into 3 climate zones. So the purpose of doing that is to make sure that we kind of installed the heat pumps in the range of climatic conditions that New Zealand has. And we're particularly interested in the performance in colder climates, which is down in the darker green you'll see in the middle of the South Island there. So we've also installed products in a range of household sizes, so right from 1 occupant all the way up to 10, and we've replaced a range of existing technologies as well. Trying to flick to the next slide, Carolyn. So we've got some good insights from the program so far, and we're sharing things as we go. So in May, we published our first report under the program, which summarizes some findings from a market scan that we did in late 2024. So that report covers insights on available products and claimed performance, which we'll of course test, and also the importers and manufacturers in New Zealand. So we did find that while the market share of heat pump water heaters is quite low, there's quite a few importers and manufacturers in the country. So there's at least 18 importers and manufacturers, and across them there's about 40 different models of heat pump water heaters available. And we also found that the main barriers to uptake are capital costs, consumer awareness, and installer awareness and training as well. Next slide. So all of our products have been installed now, and we've started some analysis on the data that we're getting in. So we are publishing an interim findings report in the next month or so. So keep an eye out for that. But in terms of some initial high-level insights that we've found, we found that costs varied quite widely. So that range for the products that range from $1,900 all the way up to nearly $8,000. And then for installation, that ranged from $1,600 up to nearly 10,000 as well. And that's impacted quite a lot by the complexity of the installation. So depending on how much building or additional plumbing works required in that specific situation, we saw quite a fluctuation of costs. We also found that installation quality is really important. So correct sizing of the tank, in some cases where that wasn't done properly, that affected the service of hot water for the household. We also came across the fact that there's quite a few additional considerations for low pressure changeovers. So things like considering increased water flow and the impact that that might have on existing piping. The other thing that we had a lot of feedback on was noise. So quite a few people found the units were quite noisy. So, alongside that, just making sure that the outdoor units are placed in an appropriate position for the household is really important. In terms of initial performance results, overall we're finding that they're performing better than other types of water heaters. There is quite a range of product performance, and we're seeing that the highest performance is achieved in warmer climates. And we're also seeing that smaller households have the lowest performance. So that's showing that heat pump water heaters are more suitable for larger users of hot water, so more in the medium to large households, and they'll gain the most benefit from installing a heat pump water heater.
So we also thought we would just share a little bit of the participant feedback we've received so far. So one of the aspects of the study was we've surveyed people at the beginning and after they've had their products installed, and people had lots of things to say. Some people were just really, really so happy with their new hot water system. They talked about saving lots of energy. They talked about not running out of hot water. I won't read all of these out, but you can see that, some people were just really, really happy with what they got. I've also included here a couple of just kind of more neutral comments that people had. Like Catherine mentioned, there were a couple of people who were a bit worried about noise. So clearly a takeaway there is, when you're installing one of these products, you probably don't need to put it outside a child's bedroom or right up against the neighbour's bedroom. I don't actually think they're any more noisy than a space heating heat pump. It's just people are not used to them, so they don't really think about it until they get the product in, and then they're like, oh, it's making a heat pump noise. And then, the comment below there, that person just had a bit of issue with installation. I think they were coming off a low pressure system. So I think there were some little bits and pieces that were problematic there. And then I also just wanted to give a bit of a plug for the heat pump water heater installer's guide. So as a sort of an offshoot from this project, we developed an installer's guide for heat pump water heaters. Now, this is a sort of a sister document to a similar space heating heat pump installer's guide we commissioned many years ago now, which was really successful. It's that came out when space heating heat pumps were a new product into New Zealand's market. So we are hoping that this will also be helpful at this stage for heat pump water heaters. So it's really aimed at professional installers. It was developed using a technical reference group, which included various industry associations. And it covers things like a little bit about how they work, and it covers things around the climate and the sizing and how you need to think about household size and climate when you are selecting a product for someone. A little bit about refrigerants, pipe work, plumbing, that sort of thing, and also how to support homeowners to get the best out of this kind of product. So that's available on the ECA website to download freely if you're interested as well. So that is the end of our presentation. We're happy to take questions later when it is time for questions. But yeah, thank you very much.
Awesome. Thank you very much, Carolyn and Catherine. That was really interesting. I've got some nice technical questions for you when we get to the Q&A from Jason, so I look forward to that.
Yes.
But
Awesome.
no, that's really, really good to have those resources as well. So thank you very much, Lee and Eddie, for putting those links in the chat as well. Beautiful. Okay, so we're going to crack on with our last speaker now. Jason, I'll just hand straight into you, mate.
Fair enough. I'll see what I can do. And
Beautiful.
if stuff sticks around, I might look off to the side a bit as I'm playing with Excel and everything else. So I apologize for that. So I think everybody's familiar with sustainable engineering, what we do. Mostly pass-fail certification will be appropriate for this audience. We do get quite into the weeds with lots of technical things. And today I want to take the opportunity to kind of go through heat pump tools, because there's a lot of tools available to us as pass-fail designers, and it can be quite confusing. So first of all, some people think the heat pump focus on PHPP is a bit over the top, but it's really quite important in why we put effort like this onto heat pumps, because pass-fail planning package is a design tool, right? The whole point of it is so you can, as an architect or a designer, as a non-building science who loves Energy Plus or detailed computer modeling person, can you design a building that performs really well, right? And you can design for comfort and for energy efficiency because you can understand how the hell stuff works, right? So pass-fail planning package is a design tool. So putting a shack size heat pump in a Jemmy Fallon kind of size house, which is what a pass-fail is a lot of times, is a bad idea. And if you do that, you'll see that the COP in your PHPP package, if you've modeled the heat pump correctly, will show that you've got really crappy COPs, like well below 1 in some cases, in a lot of cases actually, because the heat pump's much too big for the way that the pass-fail planning package assumes you're going to run the house. And we'll get into that a little bit. Yeah, so the point of modeling the heat pumps in such detail in PHPP is, and it actually is quite crude modeling to a good level, is to allow you to see what the hell's going on and make it better, right? So this is a good example, and Steve Beltran sponsored it, so I figured I'd throw some stuff in. So I've been trying to get this drawing for years from a supplier, so I'm really glad that Steve Beltran stepped up and made that happen. So thank you for that. So this is a normal, it could be an electric cylinder, but it's actually a heat pump hot water cylinder from Steve Beltran that would sit outside or in your garage, generate hot water from pumping energy from the outdoor into the heat pump, and then water comes out. And it's not uncommon in many certified pass-fails, or even just pass-fail performance level homes, to have the master suite, bathroom, and kitchen in one spot, and then the ensuite way the hell over on the other side of the building. All right. When that happens, people who are designing for comfort and a bit of luxury will often put a recirculation loop in. And in PHP, if you model it properly, you'll see that that hot water heat pump cylinder, as a system, that building with the recirculation loop has a COP of like 0.1 or even less. And that's because so much heat's being lost from that circulation loop. So you can be a clever designer, and this schematic here enables that clever design. So it has a recirculation pump that returns hot water from the fixtures back, but it only runs in this particular case on demand. So you have a light sensor in the bathroom, let's say in the remote ensuite. So when they step in the ensuite, the pump comes on. So when they turn the tap on, they have instant hot water, but the loop's not running except when they're in the ensuite. And the water coming back to the pump is cold, right? So there's clever ways to design things. And because we model these heat pumps in PHP, if you don't model them, you can see this and do better. Otherwise, you just have to hope that what you design is correct. This is important enough. We've actually had passive houses where people have torn out recirculation pumps to get certification, by the way. So they'd already paid for the pump. They've paid for all the pipe work. They put it in the building, and then they go to certify it, and you're like, oh, we didn't model it properly. Now at final, we are putting it in, and it's way too much energy. We can't certify it if we leave this in there. So we're going to take the pump out. And I've had to get photos of some very sad builder with pump torn out and a piece put in, and a photo of him holding his old circulation loop pump that somebody paid a lot of money for and doesn't get to use. That means now they have a long wait to get that water to that remote shower. So they don't get the recirculation pump benefit, but they're paid for it because they're trying to reduce energy. So I encourage us to think about that. Right, so there's benefits. All right, the other thing to think about is this is what we mean and when we speak of things, they have very discrete technical meanings, right? So when Steve Beltran, or ECA in this case, talks about the COP of a heat pump for a hot water cylinder, where they're measuring that COP is really, and exactly how they measure it is super important. So that's why we have good engineering standards in New Zealand that allow you to compare one heat pump hot water heater against another one, or an electric cylinder or domestic gas, whatever. But those standards are written by committees, and I would say that perhaps they end up with higher COPs than you would have in practice. And the way they do that is they have a large water draw. And in this picture here, which is swiped from the Steve Beltran site with their permission, they measure the COP for this cylinder basically at the hot and cold water taps. So basically how much hot water is provided, how cold the cold water is going in. And so it's like the whole tank. So the tank losses are lumped in there. The usage of hot water, that energy is counted towards the COP. And that kind of thing. So that COP number you see on a brochure for a monoblock heat pump water cylinder from Steve Beltran and from any other supplier actually, is all this stuff's lumped together, right? But in PHPP, we want to break this apart. So you can specify a better insulated tank, or you can say, oh, this household's a low demand household and has very few people in it. So there's a very low water draw because you only have one occupant in this little house, right? So the COP of the system will move around in reality. And PHP, because it's attempting to predict reality accurately, not just be a code compliance tool, is trying to mimic that, right? So you need all the pieces, and we'll take a look at that in just a sec. So Passive House Planning Package actually wants the COP of the heat pump bit, not the whole tank, and not including the water demand. So that's one of the biggest things to kind of get in your head. It also means that if you want to put a hot water heat pump system or an air source heat pump system into the building, you have to know how it works. Like, you have to know how the pieces go together. It's pretty straightforward, and we'll look at one in a sec. If you measured at this water source here, which includes any water demand being used for useful things, losses through the tank, and all that stuff, when Brands did a study on hot water heat pump performance levels, they found COPs pretty low for the whole integrated system. And basically ones that had low water usage in the building, as I think Caroline just said actually, had quite low COPs, like down to 0.5 in some cases. And the best performing one, which had quite a high demand on water relative to the other ones in this particular study, only had a COP of 2. Right? So not 4 or 6 or some other number you see from the supplier. Right? And that's not because they're lying, because they're very careful how they measure this stuff, but because they mean different things. And it's important to catch that. Right? So this is a picture from Joe Life, so from Well Architecture. I just stole it and told him I was going to use it, and sorry, I'm glad he gave me permission. So this is a relatively complicated domestic hot water heat pump system. So it has an outdoor unit that uses a refrigerant to move heat from outside the building into this little aquacore box, which then has a recirculation pump that basically pumps water from the storage tank through it to heat it up and then put it in here, right? And then it goes off here. So the model that's in Pascal's planning package, which is why I liked this graphic and swiped it, was basically you've got the distribution to the user in the end, like going to the shower and there's sinks in the kitchen, all that stuff. And that's modeled by putting in pipe lengths in here. And then the usage of water is modeled by basically by picking the TFA of the building. It assumes occupants and assumes no occupants, the water usage, but you can put in custom water usage as well. And then the heat loss from the tank itself and the piping to the tank, which can be reasonably high actually, because the tanks are quite well insulated and plumbers have an allergy in general to insulation on pipes. Pipe work is beautiful. I do know that it's pain to cover it up when it's so beautiful, but its insulation is important. So that's covered up in this part of the sheet over here with the storage losses are taken care into account, right? And then this little loop from the AquaCore box to the tank and back again, which should be super insulated, by the way, because it's got probably over 60 degree water in it, and when it's running, right? That's handled by the circulation loop stuff up in here. And then finally, the heat efficiency of basically getting that heat from the air outside into the building is handled by the component sheet where we actually have the heat pump performance. And that's why it's broken into these pieces, because then you can look at each piece and muck with it to see what's going on. Like, does it make sense to super insulate this pipe work? Yeah, you'll find out that's super important. You need to know what's the circulation loop time that's typically used by this pump to put it in as well. So the reason it's complex for heat pumps in PHPP is because they can be complex systems, and this is a particularly complex one. Okay. Certification. So PASO certifications we do in our office. We've got 4 certifiers, and we tend to, there's basically, in the certification requirements, it says basically you have to have heat pump data now with PASO planning package 10. You cannot use the standard heat pump for certification. You can use it for early design, you're welcome to, but because it auto sizes, it'll give you a high COP because it will assume the heat pump sized correctly for the load, not what you've actually installed. So that's why you need to use actual heat pump data for certification. And I'll show you a tool to do that quickly in New Zealand for split systems for heating from air source to air source. Unfortunately, the hot water systems are still going to be a bit of work involved in that. So for the heating, you need to have at least 3 test points, and for cooling, you need at least 1 test point. And I'll show you that with a tool in a sec. We'll get to that. In Pascal's plan package, there's 3 types of heat pumps that it can handle. Compact units in the component sheet. The compact units, which basically is, I forget now, it's down south. Anyways, it's nylon P, the nylon P, right? So it's got a hot water cylinder and a heat pump integrated that goes inside the building and an MVHR all in one. And basically it doesn't have any external heat pump bits. They're all inside the MVHR. So it basically sucks heat out of the exhaust duct before it leaves the building and uses that to heat the hot water and potentially the building, right? The next ones are combined ventilation and split systems, but only with PHI specified data. So if you're going to use that portion of the PHP, make sure it's only good with data from PHI. And then finally, where you'll put everything for every pump you have where you put data in yourself is this section where it's heat pumps according to EN 14825 and 14511. So those standards are strictly only applicable towards heat pumps that are used for heating, right? So you generate hot water or hot air with a split system, right? But they can be used technically for anything if you've backed out numbers that make sense, right? So for a monoblock hot water cylinder, we need to have some way to generate the heat pump data for just the monoblock, the heat pump in the top of the unit, not including the tank losses and the piping losses, because that's modeled elsewhere in PHP, right? Which is why it gets complicated. And this section here can technically handle sources of outdoor air, ground source, as well as a ground sheet if you want to do ground source heat pumps. And for dumping the heat into the building, you can dump it either to air or into water, right? I've got all these resources. I'll make sure these slides are available at some point, but they're all online. Basically, we'll talk through 3 different tools in just a minute so you can see how they work, and then we'll get into it, right? So in PHPP, there's the heat pump data requirement, which goes on the component sheet in PHP. And you basically give it a name, which can be anything, a text field, and then start entering data, right? If you have, there's also this heat pump tool available from PHI called the heat pump tool, which was designed for Europe and America. So it's built around those standards. And if you have a heat pump that is built and shipped to those markets, you can put in basically just 2 numbers, one for a couple numbers, basically just the COP, the seasonal COP for heating for cooling, and some size numbers, capacity numbers, and that'll then spit out all the data you need, right? Unfortunately, in New Zealand, we do not have heat pumps, either for hot water or for heating and cooling, that are designed to these standards. And the heat pumps, even the ones that are the same model that they sell in Europe, tend to have different software and different coolant loads put in them to come here. So basically, the manufacturers told us they're just not equivalent. So you can't use the PHI heat pump tool, which is a shame because it works quite well. It unfortunately gives you data that's just bogus. So the way we talked about 5 months ago when we did the last heat pump webinar for PHINZ is basically you get the technical manuals and you can put the data into this verification tool we've made, right? So we've got a heat pump data verification tool we've got, which just means you can put the data in and check it easily. Basically, it plots the data, which PHPP plotted the data for you. So you can see that the data makes sense and how to check it, right? We've also got another tool we've built, which is this thing we call the MEPS tool. So folks may not be realizing this, but in order to sell a heating and cooling split system heat pump here in New Zealand, you need to put data in this database called MEPS, and that's New Zealand and Australia, because we're a unified market, right? So that MEPS database, which is available publicly as a CSV file, has a lot of data in it. So we've built a tool that looks like this, and basically, if the heat pump's in there and has enough data, it has 3 heating test points and 1 cooling test point, then it'll show up in this drop-down list, which I'll pull up this sheet and show you how it works in a sec. And you can just basically pick it, the data comes up, and you can cut and paste the data into PHP. So we'll do that live in just a sec. I'm showing you this in case the live demo doesn't work, because shit always goes wrong, right? So this sheet here is designed to be printed as a PDF. So ideally what you would do is you'd pick your heat pump, hit it in, put the data in PHP, and then you'd print this just to a PDF and submit it with your certification. So then you're done, and you're done in just a couple minutes, right? Which is the goal, because then the heat pump data is in the PHP correctly, so you can see what sizing impacts have, and the data, and you're done quick, efficiently, right? It doesn't take a lot of time. Unfortunately, it doesn't cover hot water heat pumps. I'll see if Steve Electron and a few other vendors perhaps can work to put the data in another sheet for us, right? And this is embedded in the MEP sheet. We don't need to go through all this, but basically it takes this previous page here, which is the PDF, and just says, well, this number goes here on the components database sheet. This numbers go here, like just where they go. So it's really straightforward. I think it's easiest to do things correctly once. So let me show you what that MEPS database looks like. MEPS tool, this one, right? So this is what the Excel tool looks like. If I shrink it a bit, I can make it fit on the screen. So this is the MEPS tool. That's a PDF page. And there's the instruction page, which we won't look at. Oh, actually, I guess we should look at this as well. So I'll make it a bit bigger so that we can see what's going on up over in here. So this is just a way to search the database. There's 3,687 heat pumps in here that you can just pull the data in. It'll be right format. I think there's like 4,500 in the total database. So most of them have enough data to qualify for this tool. Oh, I should point out that the tool is crap. Like, it doesn't actually do anything magical. It just takes the MEPS data, checks it to make sure there's enough data for the heat pump you want, and puts it in the right format. It does, and it's the least amount of data you're allowed to use for certification. So it just meets the criteria. I sent a copy to Dr. Jürgen Schneiders, who's kind of like godfather of PHP in Germany. And he's also the head of certification services at PHI. And he's fine with it. He's like, yeah, it's about as good as you can do with what you've got available, unless you can get full test data. So anyways, so in here, what you do is you can put in a size, like if you change this to 1 for the minimum heating, then you just basically grab the brand. Steve Electron won't have any, but we'll switch to Daikin maybe. Fujitsu, right? And so you can see these are all the heat pumps available that fit in this cooling space. And if you pick ducted or something, it'll show a fewer number, right? The key to remember here, and the reason I'm doing this live, is just remember, if you want everything, not ducted or non-ducted, just delete it, and then you'll get more, right? And if you, yeah, obviously that's it, and that's how that works. This is just to give you these names so you can see what the hell is in the market looking at size. It's just a filter tool. Also, I should point out this tool is written for the latest version of Excel, unfortunately. So you need Excel 2021 onwards. And for some reason, it doesn't appear to work in Macintosh. So if you've got a Mac and you're running Excel for Mac 365 and it works, please let me know, because so far all the testing we've done with Macintosh computers, it doesn't work. So I apologize. I've gone through it. I've spent a couple hours on it trying to get it to work, and I can't even find why it doesn't work. Everything I look at says it should. So I'm a bit stuck. All right. And this is the actual sheet you use. Making it bigger so we can just look at the displays for a second. Again, you basically just go up here and pick the brand you want. Let's go up and pick Daikin in this case, just because they're not here. And then you've got to pick up model. So these are all the models you can pick in Daikin. You can see there's a bazillion of them because nothing's listed. So you pick one and that's it, right? Now all the data is here and you pretty much just cut and paste the data. And the idea is you might put over here, like, I don't know, X project, my name is Joe, or I don't care, whatever. And then basically you can only edit these green fields. Everything else should give you a warning message if you try to touch it, right? And then you just basically print this to a PDF and turning in certification and you're done, right? So at least the split air-to-air systems should be straightforward now because they've just been driving me nuts forever. All right, in the last couple minutes I've got, I'm gonna show you a couple other tools because I think that makes good sense. So let's do that. So we've talked about the MEPS tool, which if you go to our website and just go to MEPS, it's available for free. You just click it and download it. There's no cost or anything. We're never going to charge for it because we didn't put any work into it. Well, we haven't put much work into it anyways. I do ask that you try not to share the file. Please just share the URL where it's at so you can download it again in case we fix it. That's about it really on the MEPS tool. All right, so now we'll talk about the multi-heat pump tool. So if you have multiple of the same type of air-to-air split system, like 2 high wall units in the house in the same model, you can just put 2 in PHPP. It's pretty straightforward, right? It's pretty easy. If you have 2 in slightly different models and one's got a worse COP than the other, I'd be tempted to just put the worst one in and click 2 again and put that as a justification when you submit certification. But if you've got a building that's got a couple different ones, or you've got a fairly complex VRF system, then you can use this tool that PHI has called the multi-heat pump tool. It also allows you to do so it lets you do fairly complex heat pump installations. And basically what it does is it computes an overall effective COP. So you actually have to have a PHP done before you play with this tool. And it links to that PHP file because it's actually looking at that building in that climate that you designed and says, with this array of heat pumps, what's the COP curve look like for that building, right? So it's a relatively complicated tool from somebody who loves PHP and thinks it's quite straightforward. So just be aware. And I can give it to you, but only for specific projects. So if I'm going to work on this particular building with this thing, Jason, I need it, fine, I can send you the tool, right? But you can't have it to work on all future projects because it's a beta tool and that's how PHI told me to hand it out. So that's what I'm doing. So yeah, I won't get into any more than that. It's available. You got a complicated situation with multiple heat pumps and you don't want to just use a conservative assumption to make it easy, then this is the tool to use. All right. I do want to point out a couple more things and then I'll finish. So I'll go over. And once you've got heat pump selected, do realize that zonal heating and cooling loads can cause some comfort complaints for clients. So if you've got a single high wall unit in the lounge, you can cool the lounge. But remember, the MVHR will not distribute cooling, not at all. PHI's kind of rule of thumb is there's a 1-door rule. It's not really a rule, but roughly if you've got a lounge with a bedroom that opens directly off the lounge, the bedroom will get cooled by the lounge. If there's a hallway, a door to the hallway, and then a door to the bedroom's probably not going to get cooled by the lounge. If it has lower glazing ratios, the lounge has most of the glass, that may be just fine, right? If you've got a client like I typically do, where they'd like the bedroom being a degree or 2 cooler than the lounge in the winter, and you've got your heat source in the lounge, the heat recovery system will recirculate some heat back to those bedrooms, but they may still need some point source. So do realize that on more complex projects or projects where the glazing ratios are quite different in different spaces, you probably need to think about doing zonal heating and cooling loads. We can do that. A lot of those equipment suppliers have the ability to do that. They don't often do it unless you absolutely force them to, because it's not super quick. It's not terribly expensive. It's like, I don't know, 4 or 5 hours work kind of thing on a typical building. But do realize that is something to do, especially if you're going to the expense of putting a ducted system in, right? Oh, November. So yeah, for some reason, my girlfriend thought that was funny. So I thought it was funny and put it in. The other thing I want to tell folks about is that in Feb of next year, a lot of this heat pump stuff I've been doing has been especially when I'm working with Steve Lautron and stuff, has been working on a retrofit book for New Zealand. So a retrofit guide, which is being funded out of ICA, surprisingly enough, through NZUBC and then to us. And as part of that, out of that, I've agreed to hold the retrofit expert course next year in Feb. So it'll be the first time it'll be held in New Zealand and Australia. And it'll be online live, and we'll have that then. It's an odd class because it'll be half the class. So it'll be 4 weeks in total, and the first 2 weeks will be for tradies and designers, and the last 2 weeks will be just designers. So yeah, just wanted to let folks know about that. Was there anything else? Nope. And then just the resources slide, which has links to the MEPS tool, how you get the multi-heat pump tool if you need it. Pointing out again, the PHI tool is not terribly useful. And and if you want to source the correct technical data from, well, there's a lot of suppliers that do provide it, you can put the full set of data in PHP 10 by hand, and that's diagrammed quite well at this location. All right. With that, I think that is all I wanted to chat about at the moment. I'll put it back to Joe.
Sensational. Thanks, Jason. That resource is, yeah, thank you very much from me and probably from a lot of the designers online as well. That's going to make life a lot easier having that in one place. Awesome. And we've had some love for your Mo as well, so that's all good. Cool. Well, keep putting your questions in. Nikki, would you mind just highlighting all the speakers just so we can get them all on screen so we can start talking, asking some questions when you get a sec? So, one question I had, which I think Richard sort of answered in the chat, but I'll be interested to hear from you guys. Is there much of a performance difference between the split systems and the monoblocks, basically? I don't know who would like to. I mean, Carolyn, maybe you could talk to that quickly.
Well, we could talk to what we've found so far, which is, I think, so far, not really
Okay.
between the two main types.
Cool.
Yeah.
Sorry, Jason.
Yeah, just so the all-in-ones are more idiot resistant. Like you can still screw them up pretty badly, especially if you put research on them. But the split systems can be put in horribly and efficiently. The ones that are probably the worst are, I won't say particular brand, but the hydro boxes, where basically outside there's a box that sits outside that generates hot water inside the box, and then it circulates through a loop to inside the hot water cylinder, right? That's pretty common. And like I said, we've had plumbers that are pretty allergic to insulation on a number of our jobs. So I certainly have had a past house job where their water heating was several times more expensive than their old resistance tank, because their old resistance tank sat inside the house in their old villa, right? And they considered the waste heat from it free heating, right? And now the tank's inside still in their flash new passive house, but they've got a hydro box outside which had quite a bit of line length, and quite a bit of that line length was not insulated. So just, yeah, the split systems are a little bit less resistant to stupidity.
So around the design of the systems, I suppose, is a good question. We've got this design guide, which is awesome from ICA. But I suppose in your experience, is there an expectation that the passive house designer should be designing this, or is the plumber designing it, or is the supplier designing it? Where's the kind of responsibility lie with sorting out the systems? And obviously a designer will have to decide where they're going to go, but is there kind of, like with a ducted system, you can ask for a shop drawing, for example?
I guess one thing I sort of find interesting about this is that there is kind of the need for more different types of people when you're installing a heat pump water heater. So particularly with the split systems, you need someone who is a refrigerant handler, you need the plumber, but maybe you also need an electrician, or like it's a bit more of a multi-trade situation compared to how it is when you're just installing a electric storage tank. So I think it's, I think different situations though, different people take the lead. It's an emerging situation. Yeah.
Difficult, isn't it? Because people like to keep things simple, but sometimes things aren't simple. You just need somebody who knows each bit to put it together, basically. Like on a build, you need an engineer, and you need a geotech, and you need an architect, and you need sometimes you just need a specialist for each job, and trying to do it cheaply and quickly will just end up with potential for issues further down the line, shall we say.
I think that's kind of, you go, Jason.
That's right, Carolyn. I could speak.
I was just going to say that was kind of part of the thinking behind the installer's guide, really just trying to lay out some of these kind of basic things. Just, I think over time, once this becomes kind of a more of a mainstream product, these issues will disappear. But just sometimes people just need a bit of a checklist of things to think
Yes.
about before you walk away from the site.
Absolutely. I mean, we've got family in the UK, and I can see heat pumps are relatively new in the UK market. A lot of them go to whole of house radiator heating systems and things like that. But there's a lot of chatter about how absolutely shite, if you excuse my French, some of the installs are, because they just don't get it. They think you just bang it in and walk away like a gas boiler, but it's just not the same, basically. Yeah. So I think we're actually ahead of the game with that one in New Zealand, which is pretty cool. Cool. I'll ask some questions that are in the chat rather than maybe not,
Joe.
Jason.
So one point is the you're right. As Richard Walken pointed out in the chat, the all-in-ones tend to be more edit resistant. They do go in more like a standard resistance tank, more like you don't need a Friggy, for example, right? And the thing I want to point out is all mains pressure tanks, because this hasn't penetrated consciousness in New Zealand. They all have steel. Almost all of them are steel tanks with glass linings, so they almost all have anodes. The Stiebel Eltron tanks, because as sponsors, I'll throw a good word their way. Might as well be nice once in a while. Those have electric anodes, so you don't need to replace them. But most cylinders have anodes. And my experience back in America was, if you replace the anodes regularly, the tanks last pretty much forever. Like you replace an electric element or something, right? But if the anode disappears, the tank is worthless 3 months later. Like it's not like a year later, it's like 3 months. Like once the anode's gone, the tank's gone, because the steel will just corrode and it's quite thin, so it just goes away real fast. So the anodes, it's not hard to replace anodes, but it is like people are I've even had plumbers who didn't know what they were supposed to do,
So was that kind of part of the studies, or Carolyn, exploring any maintenance that might be required and making sure homeowners are aware that needs attention, like your MVHR filters, it needs checking?
Yeah. I mean, we're not specifically studying that, but we did in our sort of whole process, we did ask different suppliers what their maintenance regimes were, and there were varying answers from none to here's a 3 monthly schedule. And so for our products that we've installed, we are carrying out whatever the manufacturer has specified.
Cool.
It seems quite varied.
Question from Jason to you while you were chatting. How are you measuring COP?
So we are looking at the system as a whole, and we have got 2 different monitoring solutions that we've deployed, just to so we can kind of compare, see how the different monitoring solutions, if they're aligned. We slightly vary depending on the tank configuration. So they've all got various flow meters and water meters. Some products have temperature probes within the tank. Some didn't, like probably 3/4 don't, but it's kind of like a slightly mixed bag. But we're trying to get as much information as we can about each tank that's installed.
Cool.
So did you guys use heat flow meters or just thermocouples and water and fluid flow meters? Do you know? Because heat flow meters are like a couple orders of magnitude more efficient, right? Well, more accurate.
Yeah. So I have our very, very deeply technical engineer who was working on the design of that wasn't able to come today. As I mentioned, he had he's got a new baby in their family. But if you have some specific questions about that later, I can totally pass those on and get you some if you're interested.
Sounds like a coffee is in order.
Might do.
Cool. All right, I'll crack on because there's a few more questions. I don't want to run out of time. There's a few questions around refrigerants, and I find these really interesting as well, because obviously good old CFCs for us 80 kids. We don't want to start pumping all sorts of crap into the atmosphere again. Would somebody, maybe Bawash, would you mind explaining the difference between the different refrigerants? You know, propane, CO2, R134, R32, etc., And
Yeah.
I know there's legislation coming into New Zealand to begin phasing out all the older refrigerants. Yeah,
Yeah,
please.
no, definitely, Joe. The main types of refrigerants that we have in circulation in the market right now is the R134A, which has got a higher GWP of 1,300 something, 46, something like that. Then the propane or R290 is getting more and more common, which has got a GWP of only 3, right? So even if you lose it, wouldn't matter that much actually. So CO2 is another one, which is good for hot water heat pumps. CO2 has a special characteristic that it is a very high pressure refrigerant, so you actually have to pressurize it quite a lot to get that energy. It also differentiates itself from the other refrigerants in that it is what we call a single pass system, right? The CO2 heat pump is a single pass system. That means you basically send in the water, for example, 10 degrees to 15 degrees cold water into it, and it actually brings out water at 65, 70, 75 degrees. So it basically does it at once, a single pass. You can imagine that it cannot do a lot of it with that 4 or 5 kilowatt heat pump. So the flow rate through the unit is quite small because you're heating the water by delta T of 40, 50 K. Whereas the multi-pass system basically does that in multiple pass. So basically, so each pass it can increase the temperature only by 7 to 10 K. Right, so those are the main differences. But we also have to see that the CO2 heat pump, of course, if it gets that 50 K, so if it gets to raise the temperature by 50 degrees, it is awesome. It has got really good COP. But if you do not manage that high delta T, the CO2 is really bad. So some of the drawbacks of that as well. So I mean, both systems are really good. But of course, you have to understand what are the specialties and what are the drawbacks before installing them.
Cool. Does it matter about the climate? Depending on refrigerants, like a different refrigerants more suitable for colder climates or warmer climates and things.
Yeah, definitely. I mean, all of them have their minimum maximum. So basically, I want 134A. We're talking about -5 to +42 degrees, right? CO2 I think goes is around. Do you know, Jason, exactly what is CO2? I'm not quite sure about that.
It's the one that goes to the coldest. I think it's good to like -20 or something.
Okay. So that goes a bit colder. And the other ones, the R410As are also about -20. Propane is -25. Yeah, on that range.
Yeah, I think that probably propane would become of its own even in colder climates than that, because it's application. Yeah, so this is another one of those, when I was talking earlier about it's really complex to model these systems, or it can be. So like once you switch to a CO2 system, you basically can't use PHPP, right? Because the temperature points, it matters more that you haven't destratified the tank in a CO2 system than almost anything else. Like the outdoor temperature is less important than you haven't destratified the tank.
Totally.
So how you program that system and how it's exactly plumbed together, because they're all custom, because the CO2 systems are in hydro boxes, because the refrigerant lines are welded, they're not fitted on line. So the CO2 is not ever done by a Frigie. Like Frigies don't do the CO2 lines. Everything's welded in the box. So yeah, so it gets messy. So like the software actually matters as much the efficiency system as a refrigerant and such. So one of the CO2 equipment suppliers, Apricus, I think it was, anyways, they did a heat flow meter monitoring on the system, monitored data through a winter cycle, and we sent it off to Germany and had them. Jürgen went through it. We ended up with a COP of around 3 for that, but it's totally, it's very much dependent on everything else, so it gets really messy. Yeah.
Fun. Question from Jonathan, I think it was to Ika. Any findings from your pilot related to the use of heat pump water cylinders for demand flex?
That is something that Ika is really interested in. So, and I guess across that whole kind of water heating space generally, I guess obviously, people will be aware that ripple control has been a thing for many years in New Zealand. And when we when we scoped this study, we did ask suppliers to provide information about controllability, and the answers did vary. And some, for the kind of traditional ripple control, some can respond to the signal. Some really should not be used in ripple, with anything that's connected to ripple control at all. And there are a few products on the market where they have onboard systems. EECA's also kind of looking at some other projects at the moment where we are taking existing electric storage water heater products and popping a control system on to see how that affects the energy use of those products as well. So just thinking about different ways to approach the issue of controllability and demand flexibility. We've got our a consultation document, a green paper out at the moment, which people might be interested in, which is focusing on product demand flexibility and what we should do and where New Zealand should go in that space. So perhaps we can pop a link to that in the chat in a second as well, if people are interested.
So just for my understanding, because I sort of half get it, so demand flexibility is all to do with when we use energy and when hot water uses a lot of energy. So if we can time that to not hit the peaks and troughs of the grid, that can help the whole country kind of run better as a system, essentially. Is that right?
Yes, absolutely. And I think
Cool.
What's also interesting about these particular products is that so and hopefully something we might be able to find out in our piece of work that we're doing is that if you think about demand flexibility, usually what people are trying to do is move the energy use to essentially the middle of the night, really, a lot of times in New Zealand. Now, a heat pump water heater is most efficient and effective when the ambient temperature outside is the warmest, right? So if you've got a winter frosty night and New Zealand's electricity usage is, just right hitting the sort of peak for the year, and you're sort of thinking, right, well, I'm just going to turn off all these hot water heat pump water heaters and move it to the middle of the night. It might be good for New Zealand, but it might not be quite so efficient for the owner of that product. So there's a kind of like a trade-off there, which is something that we're really interested in researching to understand, actually what is that?
Absolutely. I mean, we've got a heat pump hot water, a Stiebel Ultron heat pump hot water cylinder at the back of our house, and it's great. It runs away. We're very rural, so it gets very quiet in night. So every now and then you can hear it, but it'll only be kind of the cooler nights. You can hear it kind of ramping up outside, sort of thing. So yeah, more a comment than a question, really. Cool. Might be Jonathan again. Have you reached any conclusions from the pilot between split and integrated heat pump hot water cylinders around upfront cost, installation cost, and complexity, performance? Which one wins, I suppose, is a simplification.
I don't think we have yet. It's still a work in progress. I don't know if you've got anything further to add on that point, Catherine.
There will be some information on that in the interim report that'll be coming out shortly, but I think overall, on average, split were more expensive. But there'll be a more detailed breakdown about exactly what that looks like
Cool.
coming soon.
Awesome. Yeah, I'm going to leave Mateo's question to the end, actually. So, my question for you, Jason, is do you have any recommendations as to, after my conversations yesterday, what to ask suppliers for around the data to enable us to put hot water heat pumps into PHPP so they don't get confused and so I don't get confused?
It's going to matter depending on the system. So, yeah, so that's, yeah, sorry, there's no other way to do that, right? So, yeah, because we're talking, if it's generic questions can only get generic answers, you got to figure it out. Right? The first step is doing what you did, which is looking at how the different pieces get modeled in PHP. So the piece you need is what is the COP just for the unit that uses refrigerant outside and dumps heat to the inside of the tank? Like, what's that COP curve look like for test points? And unfortunately, the New Zealand test data doesn't give us that, right? It only gives us the full integrated system with different demand cycles. And for really high demand, you get quite good COPs with these systems. And for really low demand, you tend to get shitty COPs, right? Interesting thing is, I'm pretty sure that the resistance electric tank would even be shittier than the shittiness scale. Like it'd be even worse, right? But we tend to think of electric tanks as COP of 1, and that's not true. They only generate the hot water as COP of 1, right? And then they have the same losses in the tank and the pipes and such. So that's something that probably, actually, I'd recommend that you can make sure you put that in there, because that's not obvious to folks, that the COP of 0.7 might be a lot better than what you would have got with an electric tank. But anyways.
Yeah, no, absolutely.
Yeah, so yeah, Joe, sorry, we'll have to back
No,
it
no,
up. Is what it
it's
comes
all
out.
good.
So yeah, I apologize. The and I don't, and it can take time, and you know, basically the person who pushed us into that system is your client, right? So in my opinion, that's who should pay for that time, or the supplier should, and shouldn't come out of my skin every time.
Yep, not at all.
Yeah. So
Cool. All good. One question I wrote down for Bhavesh around using heat pumps for underfloor cooling. In my mind, there'd be a risk of condensation with creating colder surfaces in warmer spaces, etc., etc. I did talk to I can't remember the name of them, a supplier that did radiant heat panel systems in ceilings, which did a similar sort of thing. And they didn't really have a simple answer. Do you have any kind of commentary on that?
Absolutely, yeah. So, so the reason it condensates is because of dew point, right? So if the dew point is not managed properly, it condensates. So what we have in our system is basically have a heat pump. The heat pump cools down the tank in summer and warms up that same tank in winter. So in summer, the tank is sitting at 10 degrees. Of course, if we put that 10 degrees into the floor, nothing really would happen in Queenstown, but in Auckland, it will start to condensate, right? Because the dew point, it's more humid here. The dew point is much higher here. So the basic thing is to manage that dew point, and how you do that is basically by mixing that temperature down with the mixing valve that we have in the heating circuit or cooling circuit down to a temperature, or actually just above the dew point. So let's say, for example, you've got a humidity of 65% in Auckland today. Your dew point is, let's say, 15 degrees. So we send temperatures into the floor only higher than 15 degrees. Right. So in probably in one of the favorite really humid day in February, if the dew point is 85%, 85% of the humidity, your dew point is 22 degrees. So any temperature below 22 degrees, you set in the floor or the radiant ceiling cooling will start to condensate. So it's basically just managing that dew point, and how we manage that dew point is we've got a controller that it records the temperature, records the humidity, calculates the dew point, and with that operates the mixing valve to send the temperature into the floor, which is higher than the dew point.
And the other catch is it means you cannot use floor coverings. So with heating, you can cheat and put direct fixed carpet down or a real thin underlay and still do it. Like, they don't like it, it's not recommended, but you can do it. But with cooling, it becomes much more of a concern, because you'll have a delta T across the floor. So you can get mold under the carpet. So just be aware that that can happen without in-floor cooling, right? Just with the slab that's cold, because there's no insulation. So if you get mold under carpet, I mean, if you pull carpets out in Wanganui, you'll see that they're all molded around the edges of the house, right? Because they've been direct fixed and they've been there for 40 years. So it's not just but it is just people will cheat and put carpet down. You shouldn't do that with cooling, even in Queenstown, because it gets messy fast. But we've done several buildings with the system that Electron sells in Queenstown.
Yeah.
So our clients are pretty happy.
Yeah, I mean, of course, tiled surfaces are the best surfaces, right? I mean, if it's a hard floor, polished concrete, definitely best way to go. But we've done multiple jobs. One in Milford in Auckland, which has got basically just your ceiling radiant pipes, and that cools the entire space. Works perfectly fine. Just need to manage the dew point.
Oh yeah, I've got one in Hamilton, which is going to be using it, which will be fun as well. Awesome. Okay, cool. Richard, I see you've asked a question about the refrigerant phasing out in New Zealand. I will find that study document, unless Carolyn or Catherine have a link they could, or one of your colleagues could bang it in the chat. But I've got it stored somewhere, but I'll find it. We'll send it through to Richard. So great question, Matteo. Tuika, $1 million question. When will the government start subsidizing hot water heat pumps? Because it just seems like an absolute no-brainer, but personal perspective. I can see the current government don't usually
Oh,
use the reins
yeah,
very
it's
often.
probably that kind of question's a little bit above my pay grade, I would say. But yeah, we're doing what we can to support the uptake and the rollout of these technologies. And I guess we're really interested in making sure that people at this kind of early stage of the rollout in New Zealand, that people get the right advice and that they are picking the right products and getting a good experience. Because if people don't get a good experience, they're not going to recommend it to their friends. Plumbers are not going to want to, install it as a replacement technology because it's just too much hassle. All of those sorts of things. We're really keen to just make sure that people get a good experience from a heat pump water heater. So
I've got a friend in, where is she? Waikato somewhere, and yeah, she did loads of research on heat pumps, ended up going for a particular brand that advertised like a copper 5.2 or something like that, installed it, for, really onto it, monitored her power, and it was nowhere near, and she was not happy, as you would imagine, so I think it's really important to make sure we're being realistic about these things.
Yeah, absolutely. I mean, the question that Jason asked as well, how the COP is measured is absolutely important because I mean, as I also sort of briefly touched upon, COP is what heat output you get out of it and what energy you put in that, right? So if there's any lag, if you're measuring, downstream the pipeline will be completely different. So if actually the heat pump unit is supplying a COP of 3, if you measure somewhere else, it might be just 2.2, and if that gets recorded, it's not really good name for the heat pump, right? So the measurement is very, very important.
And so because he's left now, but a guy from Black Diamond was on just mentioning that the test standard of heat pumps in New Zealand is AS/NZ 3823, and the in my brain is like, what is that? Is there a requirement for the amount of draw off? Around how that's tested and all sorts of things, so that's all kind of standardized within that. But that doesn't impact PHPP because that doesn't really take into account draw off, or
correct.
The way we put it in. Yeah,
we put it in separately. Okay. So if you think it was designed for electric resistance tanks, right? So basically, it's a standard that says water coming in this temp, water going out that temp. You have a draw cycle and that kind of thing. I think they've got several draw cycles. Do you remember, Carolyn? I've forgotten. It's been a long time since I looked at that standard.
I guess hot water standards. It's a whole world. There are many standards, so just as an aside, I guess. Eddie's just put 5125 in the chat and 4234. Yes. We are looking at the moment at thinking about whether or not there's a case for including heat pump water heaters into the MEPS regime. So for space heating heat pumps and for electric storage water heaters, there is minimum energy performance standards. There is not for these products right now. I mean, there are standards out there that measure the performance, which are great, but there's not a minimum.
Bit of a Wild West, it sounds like, yeah.
It is.
No, I think there's some really good products out there.
West, yeah.
Actually, there are some really awesome products out there, and that's why we really want to support this technology. It's just a case of like, I guess making sure that people have, the right advice, right information.
Definitely.
Yeah, it's just heat pump water heaters. You can have like 10 different configurations, right? And that's not even getting crazy. Like Rich will say one that's even crazier, right? He's like, we did one system where he's got like a gas califon outside as a backup to heat pump water cylinder inside, which used air from outside the building, but it's inside the envelope. And then it had solar panels on the roof as well. And I think he's got another one that does solar panels with the solar panels actually have Freon in them. Like it's got refrigerant going through the solar panels, right? That was done on one of the office buildings downtown here that I forget which agency owns it now, in Wellington. So that's got a hot water system with refrigerant. It's one that anyways. But yeah, so they're really complicated, and we're still kind of in the Wild West of all these different configurations. So trying to figure out how you do a test standard to do more than what the New Zealand standard is really hard for me to get my head around.
Yeah, because there's also like rooftop solar water heaters, which can be plumbed into hot water cylinders, and it's just kind of how many different technologies do you want to add into a piece, basically?
No. One thing at a time.
Just think about how you'd qualify like a drain water heat recovery system, right? It's a chunk of copper tubing. Like, but there's a bunch of different ways to measure it, and you get really different results if you measure it differently.
Yeah. Awesome. Well, thank you so much, everyone. We've run out of time, but that was really, really interesting. And thank you everyone in the chat as well for getting involved. And thank you for all the really useful links. Hopefully everybody's kind of clicked on those and got them saved somewhere before this ends. But yeah, just thank you very, very much to Varesh. Thank you very much to Steve Electron for sponsoring. We really appreciate it, guys. Yeah, great products. I use them.
Thank you.
Thank you very much, Carolyn and Catherine from ECA. That's really interesting. I'm looking forward to seeing where this goes. Yeah, lobby government because it's a good idea. And yeah, thank you, Jason, as ever, for your extreme generosity and input. Really cool. And thank you very much for attending, everyone. We are going to have another one soon, so keep an eye out for that. We appreciate your support. We rely on this sort of income to keep PHINZ going. So yeah, enjoy the rest of your Thursday.
All right. Thanks, everyone.
Thank you very much, team. Cheers, man.
Bye.